Hi all, welcome back. And in this video, we are going to learn about representation of relations. So obviously, we are going to learn about mathematical relations. So how we are going to represent it mathematically. So let's say we have a set A and the cardinality of set A is n. And let's say R is a relation on which is defined on set A. Okay. Now, if we represent the matrix relation, okay, so in matrix relation, what happens that we are representing each element of the relation. Okay, so if the cardinality of set A is n, so a number of entries in relation on A or the number of relations we can say on A will be n cross n definitely. So if it is n cross n, so mr is the cardinality of a matrix relation for each element, so it will be an n cross n matrix, and where aij equal to, it can be either 0 or 1, and 0 means I comma j is does not belongs to R, and 1 means I comma j belongs to R. So 1 will indicate that ij will belong to R, and 0 indicates that ij does not belongs to R. Now what does that means, we'll see in this part that is called diagraph. So we will be drawing a diagraph for the relation R, which is defined on set A. Okay. So if we have a set A with cardinality of n, so let's say each element in set A is denoted by a vertex. Is denoted by a vertex, right? And there is a directed edge from vertex I to vertex j. There is a directed, because since we are learning about ordered pair, so therefore directed edge. So there is a directed edge from vertex I to vertex j, right? If and only if ij is belonging to R. Okay, so if ij belongs to R, then only there is a directed edge from vertex I to vertex j. So let's say if in we have a set A which consists of element 1, 2, 3, 4, and let's say a relation is defined on A, not A cross A, relation is just defined on A, which contains ordered pair of elements like 1, 1, 1, 2, then it is 1 4, then it is 2 2, then it will be 2 4, then 3 1, 3 3, and of course 4 1. So these are some of the ordered pair which is present in R. So R is a relation which is defined on set A, and set A has a cardinality of 4, which consist of elements 1, 2, 3, and 4, and somehow these elements are related to each other. That's what we have shown in this relation. Okay, now we will draw it diagrammatically. We'll draw it diagrammatically using matrix relation MR, and here what will happen, each no each element of set A will be denoted by this vertex. So this is vertex I, and let's say this is vertex J. So now, if there is an edge if there is a directed there is will be a directed edge from 1 to 1 if 1 1 is present in R. So 1 1 is present in R, so there is a directed edge. If 1 2 is present in R, there is a directed edge. If 1 3 is present in R, no, it is not present, so it will be 0. If 1 4 present in R, yes, it is present, so 1. So 2 1 present, no, 0. 2 2 present, yes. 2 3 present, no. 2 4 present, yes. 3 1 present, yes. 3 2 present, no. 3 3 present, yes. 3 4 present, no. 4 1 present, yes. 4 2 present, no. 4 3 present, no. 4 4 present, no. So this will be the diagram matrix representation of relation R. Okay, so this is matrix representation of relation R defined on A, where each element of A is denoted by the vertices, okay, of the matrix, and there is a directed edge from vertex I to vertex J if there it is ij is present in R. So this is just as simple as this. So this is the matrix representation, and let's see the diagraph representation. So we have 1 2 3 and 4. So between 1 and 1, yes, there is an edge. 1 2, yes, there is an edge. 1 3, no. 1 4, yes, there is an edge. Okay. 2 2, yes, there is an edge. 2 4, yes, there is an edge. Okay, and 3 1, there is an edge. 3 3, there is an edge. 3 4, no edge. 4 1, there is an edge. 4 2, no edge. 4 3, no edge. 4 4, no edge. So this is the diagraph representation. Diagraph representation of relation R. Okay, so this is how it is defined uh, about how to represent relation. Now, there are something that we already talked about, that is inverse of a relation. Okay, so we are gonna see some of the operation on relations. Okay, so it is a common result. Let's talk in term of result. So let's say let R1, R2, and R3. Uh, let's say R and R1 and R2. That will be better. So R, R1 and R2 be the relations on R. Okay, so these are the relations on R. So if R, R1, R2 are the relations on R, so we have to find whether R inverse is reflexive, then R1 intersection R2. Okay, sorry, this is are the relations on A. There are three relations, okay, and R1 union R is what? So this is R1 union R2, right? So this is basic a comparison between all. So here we are considering that all the three are reflexive. Okay. So if all of them are reflexive, that is R, R1 and R2. So what is this R inverse? If it is reflexive, then what does that means? If A, B, all for all R elements in R, A will be present in R. Okay. So in R inverse, if we see, it is also going to be reflexive, right? So if it is reflexive, the inverse is also going to be reflexive. If it is irreflexive, R is irreflexive, then its inverse is also going to be irreflexive. If R is symmetric, then R inverse is also going to be symmetric, right? If it is asymmetric, R inverse is also going to be asymmetric. Okay, so we are considering about R. If R is asymmetric, R inverse is also going to be asymmetric, right? So because R inverse is just the opposite of R, right? So if it is asymmetric, it is also going to be asymmetric. If it is antisymmetric, then R inverse is also going to be antisymmetric. And if it is transitive, R inverse is also going to be transitive. Now let's talk about R1 intersection R2. So if it is reflexive, R1 intersection R2 is also going to be reflexive. R1 intersection R2 is irreflexive if both R1 and R2 are irreflexive, because we are taking just the common of them. So if R1 is irreflexive, then definitely if A1 and for all A present in R1, A1 AA will not be the part of R1, and AA will not be part of R2, right? So definitely their intersection will be irreflexive. If it is symmetric, if R1 and R2 are symmetric, like then uh, then definitely this will be also symmetric. And all for all we have asymmetric, antisymmetric, transitive. But if we take off R1 union R2, then there will be some changes. So if it is reflexive, it is going to be reflexive. If it is irreflexive, it is going to be irreflexive. If it is symmetric, it is going to be symmetric. But for asymmetric, antisymmetric, and transitive, it need not to be. Okay, so this is an important thing to note for R1 union R2. Okay, it need not to be this. So we can show this with an example. Let's say R1 is a relation on A, and R1 consists of 1 comma 2, and R2 consists of, let's say, 2 comma 1. If we are taking their union, so R1 union R2 will be 1 comma 2 and 2 comma 1. So this is symmetric, this is symmetric, this is symmetric. But this is asymmetric, this is asymmetric, but this is not asymmetric. So this is not asymmetric, this is not asymmetric, and this is not antisymmetric. Definitely this is not antisymmetric. And of course, this is not transitive as well. So this property will not be valid for union part. So that's all for this. We have more to discuss about the closures, basically the reflexive closure, symmetric closure, and the transitive closure. And then we'll see the Warshall's method and the diagraph method next. After that, we have something called results based upon all these relations. So we'll see them next. So till that, if you have any comments or questions, keep posting in the comment section. That's all for this part. And thank you very much for this. And do keep watching and do keep posting comments if you have any.